Take out your phone right now. Look at it. Behind that sleek interface, the smooth scrolling, those instant apps you rely on, what's actually running the show? Well, it's C. Glance over at the computer sitting on your desk. If you're running Windows, which is the world's most popular desktop operating system, you are looking at a massive digital empire built entirely on C. And the internet itself? The servers, the massive routers, the invisible infrastructure bouncing this very explainer into your brain right now, it is literally all relying on a genuinely terrifying amount of C. Welcome to this explainer. Our goal today is simple but ambitious. An ultra-informative, concise breakdown of absolutely all of the C language in just 7 minutes. We're going to unpack the foundation of reality. Think of modern languages, like Python or JavaScript, as these beautiful, gleaming skyscrapers. But those skyscrapers, they have to stand on a massive, glowing, solid foundation. And that foundation is C. So let's understand exactly how it works. Section 1, the foundation, where it began. To understand why C dictates our digital reality, we really have to look at its origins. So picture it, 1972. Dennis Ritchie creates C at Bell Labs. Now, it wasn't a commercial product being sold in stores. It was just an internal tool used to build the Unix operating system. But it was so remarkably efficient, striking this perfect balance between human readability and raw, unadulterated hardware control, that by the 1980s, it just became the universal standard. And today, modern hardware fundamentally still runs on C. It's the language that manipulates memory directly. But man, that absolute power comes with incredibly strict rules. You'll see high-level developers, the Python or JavaScript folks, react with sheer terror to C's strict syntax and its manual memory management. In Python, you kind of just type a word and the computer handles the rest, right? In C, if you forget a single semicolon, the compiler literally refuses to build your program. It demands absolute precision. All right, Section 2, Anatomy of C. The syntax pipeline. Let's make this intimidating code actually make sense. Let's crack open a classic Hello World program and break it down physically. Step 1, stdio.h. Think of this as cracking open a physical toolbox that contains your tools for input and output. Step 2, int main. This is basically the entry gate. It's exactly where your computer starts running the program. Step 3 is printf, which is essentially a message cannon, just firing text straight onto the screen. And finally, return 0. This just signals the operating system that the mission is completed. You see, it's not just text. It's a sequence of direct physical commands. But how do those human-readable words actually command the machine? Well, that's the compilation pipeline. Your source code goes into a compiler, which completely strips away the English words and translates them into machine code. Then that machine code is distilled down into pure binary, just ones and zeros. And here is the real magic. That pure binary directly controls the electricity flowing through the physical CPU registers. You're literally writing text that dictates electrical pulses. Mind-blowing, right? Moving on to Section 3, memory arrays, or, as I like to call them, physical dominoes. Let's plunge into the micro level. When you type out a variable in C, you're not just creating some abstract idea. No, you are claiming a literal physical box in the computer's RAM. Saying int age equals 19 claims a dedicated integer box. Float pi equals 3.14 claims a decimal box. The C compiler assigns these strictly defined hexadecimal addresses right in your physical memory grid. It's actual physical real estate. And that brings us to arrays, like typing nums bracket 5. Now, high-level languages treat arrays as these flexible, stretchy lists. But in C, an array is a rigid, contiguous block of physical memory. The boxes are placed exactly side by side. If you trigger the first one, the rest follow in perfectly sequential memory addresses, lining up flawlessly, like falling dominoes. It's incredibly fast precisely because the CPU knows exactly where the next piece of data is physically located. Okay, Section 4, the terror of pointers. Take a deep breath here, guys. We are introducing the most feared concept in computer science. The pointer. A pointer, by definition, is simply a variable that literally holds the physical memory address of another variable. It doesn't hold a standard number like 10 or 20. It holds the exact hexadecimal location in that RAM grid. And it is the ultimate tool, giving you this terrifying direct access to edit memory in real time. You look online and you'll literally see memes screaming, "This is where most programmers give up." And hey, it's true. The concept of managing physical addresses manually is where the learning curve spikes hard. But don't worry, I promise we're going to make this easy. It is actually incredibly elegant once you visualize it. Look at how elegantly this works in practice. Step 1, int x equals 10 stores the number 10 in a memory box. Step 2, we create a pointer, $ptr, and we set it to $x. Now that ampersand just means grab the address. So the pointer locks on to x's physical location. Step 3, we say $ptr equals 20. Because the pointer is locked on tight, it edits the original value live in memory, changing it to 20 without ever actually touching the variable x directly. That's dereferencing. You are basically a digital puppet master, pulling the actual strings of memory. Which naturally leads us to section 5, stack, heap, and leaks. Time to talk macro management. What happens when your code gets greedy? Every C program works with two primary memory areas, the stack and the heap. Now, the stack is safe. It's automatic, it's highly organized, and it cleans up after itself the second your functions finish running. But then, there's the heap. The heap is dynamic, wild, totally chaotic. It doesn't do a single thing automatically. If you want memory here, you have to manually beg the operating system for it, using the malloc command. And crucially, you have to give it back using the free command. But if you forget to use that free command, well, congratulations. You've just created a memory leak. Think of the heap like a giant hotel. Using malloc is renting a room. If you leave without checking out using free, that room stays locked forever. If your program keeps renting rooms and never ever checks out, eventually the entire hotel runs out of space, the operating system panics, and your whole system crashes hard with a segmentation fault. That is the true danger of manual memory management. Section 6, keys to the machine. Let's talk about building worlds out of these tiny manipulations. So C lets you organize all these tiny data pieces into complex structures using something called structs. We can actually define a player struct that perfectly mirrors an RPG game's stat HUD. We group a character array for the name, hero, and an integer for their health. By grouping data together like this, C can model entire worlds, physics engines, huge databases, all while maintaining that lightning-fast access. And that raw performance is exactly why C absolutely dominates the world right now. Just look at what it powers. The Linux servers hosting the cloud? C. The embedded systems controlling actual rocket launches? C. The core logic of massive game engines, advanced robotics, the underlying systems of AI servers, it's all built on C. When you need absolute performance, zero lag, and direct unfiltered hardware access, there is simply no substitute. Which brings us to a really foundational philosophy. Modern programming languages are amazing. They really are. They hold your hand, they clean up your memory, they keep you safe from those nasty crashes. But C gives you the keys to the machine. It strips away all those cozy abstractions and lets you command the raw electricity of the processor itself. Programming honestly stops being magic the moment you learn C. You suddenly realize there's no wizardry going on behind the screen, just perfectly aligned dominoes of memory waiting for your exact instructions. Once you understand this foundation, the entire digital world finally makes sense. So the only question left to ask yourself is, what will you build now that you hold the keys to reality?